So guess who's going to do some really fun population calculations today? We are. And at the end of this, you're going to feel a lot more confident, so you better strap in because it's going to be a hoot. All right. So we're going to first start with change in population size. This is going to be the easiest place to start, and it's going to give us a really good foundation for understanding other things about how populations do change. So, when discussing change in population size and using the equation that we'll get to, you have to operate with a certain assumption that immigration and immigration are equal. Okay, and that's just because if there were immigration and immigration, then we're going to have more pluses and more minuses and more equations. So we're just going to say immigration, immigration, those things, they don't exist to us. We're going to pretend that those are equal, even though in nature that's very, very unlikely. So let's go on to our first practice problem. So here's our example. An ice cube maker has 32 ice cubes in the tray. A person uses 12 ice cubes a day, and the ice cube maker makes 50 ice cubes a day. So how much does the population of ice cubes grow? Well, let's pretend that a person using the ice cubes is predation, and those ice cubes are dying because they're being taken out of the freezer, they're melting, they're gone for good. They no longer exist in the population. And the 50 ice cubes that are made by the ice cube maker a day, those are the babies. That's the birth of ice cubes, essentially, in your freezer. And so I'm just using this example because it's, I think, a little easier to remove the ecological aspect and understand why something is the way that it is, and then we can put that back later. So we have this equation that we're looking at right here. Delta n is equal to b minus d. So delta in math, that's that little triangle guy. That always symbolizes a change in something. So the change in the population size is equal to the births minus the deaths. And the reason why we can say this is because the births is how much the population is growing by at any one time, and the deaths are how much the population is shrinking by. So the change, the total change in population size is the sum of these two. But wait, there's more. There's a minus sign here. So how is it a sum? Because essentially, if you want to really break it apart, you can say that there's births, so that's the positive change, and you can add that to the change in deaths. However, because the deaths mean that there's a decrease, that means that there has to be a negative sign there. And since we know if you add a negative number, you can have births minus deaths in the end. So in case you wanted some mathematical proof, there it is. So what I want you to do now is I want you to pause this and do this equation on your own, and then start the video back up, and I will go through it. And then we can make sure that our answers align. Let's do it together. So we want to know how much the population of ice cubes is growing by. So that is our delta n that we're looking for. So delta n is equal to births minus deaths. So we have 32 ice cubes to start with. But that's not how many are being made and how many are being removed. So the 32 ice cubes that we have here, So the 32 ice cubes that we have here, we don't care about them. They are irrelevant to us right now. All we need is that a person is using 12 a day and that 50 are being made a day. So that means we're going to have 50 births minus the 12 that are being removed every single day. So if we subtract 12 from 50, we should get 38. And this 38 is not how many there are. So this 38 is not equal to the number of ice cubes there are at the end of the day. Instead, that is how much the population is growing by. And we can say that that's how many ice cubes there are being produced, or that's how much. We can say that the population is growing by 38 ice cubes per day if we wanted to, because this problem gives us a span of time. Now let's go on to the second question. This is just to get you thinking. This isn't necessarily an equation that you were given. This is to let us start thinking about what these numbers mean for us. So, how many ice cubes are there the next day? Well, this is normally a pretty specious question if we don't have all of the relevant information. However, we do have the relevant information. In order to figure out how many ice cubes there are going to be by the beginning of the next day, we need to know how many ice cubes we started with. And we do know that. That's where these 32 ice cubes that we had in the tray to begin with came from. So now we can say that the population size the next day is going to be equal to the starting number plus however many there were per the number of days. Right? Well, that means that if we had 32 ice cubes to start with, and we're looking for how many ice cubes there are the next day, which means there's only one day, we can say that we have 38 ice cubes being added over the course of that day. That leaves us with 70 ice cubes. And that's why understanding the change in population size is so important. Now, we have another problem that uses sort of the same thing. On the second day, the ice cube maker breaks. 48 ice cubes melt away every day, but a person supplies the tray with a bag of 30 ice cubes. What is the change in ice cube population? Because remember, the number of ice cubes that we're looking at is a population of an inanimate object, but we can just as easily say these are birds, we can just as easily say these are plants. It doesn't really matter. The principle is still exactly the same. So even though this is an ecological thing, you could just think this in terms of units. If you're just getting all wound up, maybe they're giving you specific species names and you're confusing yourself, just pretend they're ice cubes, pretend they're Legos, and you're adding and subtracting them. It'll make it so much easier. So let's determine what the change in ice cube population is now. So now we know that delta N is equal to births minus deaths. Now go ahead and pause the video, and when you are done, go ahead and come back, restart the video, and then we will do this together. Okay, so before we get this started, I want to caution you against something. So we have 48 ice cubes here. We have 30 ice cubes here. Do not just subtract the smaller number from the larger number, because that can be wrong. What you want to do instead is make sure you strictly define your variables. So births for us is how many ice cubes are made. So here, there is an increase of 30 ice cubes. They're not being made by the maker, but we can still pretend that they're being birthed from this bag of ice cubes that someone is dumping into their ice maker tray. So we have 30 that are being put in, and then we have deaths, or how many ice cubes are melting, as 48. So now let's put this in the equation. We have 30 births minus 48 deaths. Okay. We're going to get negative 18. This negative is super important. Do not drop this. A growth of negative 18, or a change in population size of negative 18, means that the population is decreasing by 18 ice cubes per day. All right, so now we're going to cover per capita growth rate. So I have included a little definition that you might find helpful. So per capita means per individual. So if you're ever unsure of how to represent that mathematically, remember that per is, you want to divide. You want to find how much per one person, right? So we previously calculated in our last example that delta n is 38, and 38 is the population growth, okay? And that's also equal to r, so r and delta n are the same thing. We're going to do a bit of a challenge problem in a bit, so that's a really good thing to keep in mind. So I have also included the per capita growth rate equation here, and if you think about it, it really does make sense. We have the growth rate, and then we have the number of individuals. If you divide r by n, it's how much growth is happening per individual, and that's what we want. So this equation is perfect for our uses. So let's go back to the ice cube example. So before we calculated that the r, or the delta n, they mean the same thing, is equal to 38. And we know that the number of individuals in the population to start is 150. And if we look at our equation that we have up here, we are only missing one variable, which is the per capita growth rate. So we know we have all the information we need. And so we can just plug that in. So we do 38 divided by 150, and you should get roughly 0.253. Now we're going to be doing a little bit of a challenge problem. So this problem I designed so that we can just put everything that we have just learned together. So the question reads, a population of fennec foxes started out at 130 individuals. 53 foxes were born, and 62 died over the course of 3 years. What is the per capita growth rate per year? So, if we look at our equations, I put a little equation bank for you. Let's just talk about things here. Don't let all these little equal signs that I put in here scare you. That just means that the rate is equal to the change in population size over time, which is equal to the births minus deaths that we did previously. And then we have this whole equation that we just worked with. So what I'm going to do is I'm going to zoom out here. You go ahead and attempt this problem. Pause the video now. And then when you are done, restart the video and we can do this together. All right, so the way that I like to start any problem is I'm going to define my variables. So we know that our starting population, N, which is what we're interested in here, is equal to 150 foxes. Great. Now we have 53 were born, so that's B. Then we know that 62 died. Okay. Now, there's something that we need to make sure of that we're not forgetting about. This is over the course of 3 years. We want the per capita growth rate per year. So, let's go ahead and get this party started. First, to solve this problem, we eventually want to find this variable, but we don't have big R yet. So let's go find big R so that we can plug it into our second equation. All right, so we've got R is equal to births, which is 53, minus 62. And that's going to give us -9. All right, so now we need to be mindful. -9 is not the change in population over a year. This is over 3 years. Per 3 years. Well, if we show what I just said per 3 years mathematically, well, it just told us what to do. I'm going to divide that by 3. So now we have -3 per year. And that's what that delta t is. Now we've now found the change for 1 year instead of the change over 3 years. Now it's a matter of simply plugging this into our little R equation. We have -3. I'm going to divide that by our starting population N, which is 150. And what we're going to get is a per capita growth rate of -0.02. Now, if you forget to divide in this step, I'm going to show you why that's okay, so long as you remember to do it at the end. Say we use the -9 that we got previously, and we divide by 150. We're going to get 0.06 negative. Then if we divide that by 3 now, you're going to get -0.02. So you can divide at either step, whatever makes the most sense to you. Because what we're seeing when we're looking at this is the change per year. So then we don't have to convert anything here. This is saying that there's a change every 3 years of -9. And now this is saying that there's a per capita growth rate of -0.06 every 3 years. Per 3 years. That's what we can always call this dividing sign as. And then we still get the same answer in the end. So do what works best for you. But either way, you should have gotten -0.02. And again, do not be afraid of negative numbers. I know it's really tempting to drop signs, but that's going to not give us very useful information as biologists and ecologists, because if we drop that negative sign, we're going to have very different looking graphs. Where, remember these, we have pop size, pop meaning population, of course, we have time. And remember that these are rates. And rates mean that they're going to give us a slope. If a slope is positive, which this is not, it would look like this. That's showing us that as time increasing, the population size is increasing. That's not what's happening with the fennec foxes that I did in this example. None of this is representative of what's actually going on in nature. This is purely for practice, but maybe what you can do is go find some population data on an organism of interest and practice doing these calculations with those. So we have our negative number, means we're going to have some sort of graph that looks like this, or maybe like this. Just some sort of negative sloping graph. That's what you want. All right, so let's start talking about estimating population size using a bunch of variables that you're now becoming very, very familiar with. This equation says that the overall rate of growth is equal to the per capita population growth rate times the population size. And that makes sense because you're going to take the production of a single individual, multiply it by how many individuals there are in the population, and that'll give you a good idea of what that change is going to be. So let's go ahead and do our first problem. Woo! Okay. So, a population of 1,763 spiders grows by 23 individuals per year. How many spiders would you expect in a different population of 636 individuals? Okay, well, that's a lot of words for so little information. So what are we going to do? Let's do the easiest thing. Take the path of least resistance. It'll work smarter, not harder. Let's just define our variables and see what we have and what we need. So we have population 1, which is going to have a population size, or N, of 1,763. Then we also know that it grows by 23 individuals per year. So we know that that is the population growth rate. However, what we don't know is the per capita growth rate. Now let's look at the second population. Do we know what N is? We sure do. It is 636. Know what big R is? No. There's no information on that. What about little r? We don't have information on that either. But we do have a very important piece of information here. These are two populations of the same species. We'll assume that all else is constant. So they're going to have the same per capita growth rate. So if they have the same per capita growth rate, then we know that we can do R1, little r1, is equal to little r2. That's going to really help us now. So we don't have enough variables in population 2 to do anything with it yet. So let's start with population 1 and get that per capita growth rate. So to get the per capita growth rate, we know that little r is equal to big R divided by N. In other words, the rate of growth divided by the population size. Now, if we divide those things, 23 divided by 1,763, we're going to get roughly 0.013. And that's our little r. Well, wait a minute now. Now, we can fill this in for population 2, little r, because they're the same. So we can make sure that we fill in our little chart that we have. Fantastic. Now we have enough information to find out how much the other population grows by. So to do that, we're going to use our shiny new equation, sparkle sparkle, to find out how many individuals this population grows by unit of time. So we know that R is equal to little r times N, which is equal to 0.013 times 636. So 0.013 times 636. And we're going to get 8.268. Now, this isn't where we stop. This is only big R. We want to find out what nt plus 1 is. Nt plus 1 is basically saying we had the starting population of n, and we've moved forward 1 unit of time. And in this case, it's going to be 1 year, because we want to know what the population is going to be this next year. So in order to do that, it's very simple. We take R, and then we add it to the original population. In other words, we're going to take our new number, 8.268, add it to 636. And if you do that, you're going to get 644.268. Yes, I know that you can't have 0.2 of an individual, but bear with me. I'm leaving this number with so many significant figures because I want you to see why what we're doing next is the only right way to do it. So we're going to do it the right way first, and then I will show you why the wrong way is wrong. So hopefully we don't make that mistake. So let's go to the next part. How many spiders would you expect in the population in 2 years? So this is asking about the population 2 that we defined earlier that started out with 636 individuals. Well, we need to know how much the population grows by. And remember that that growth rate is R equals the per capita growth rate times the starting number. Now here's the thing. Our starting population now has changed because we're now going another year into the future. That's why we're going to be finding nt plus 2. We're going another year into the future. So what we're going to have to do here is we're going to have to find R again. So R is equal to the per capita growth rate, the magic number 0.013, and you're going to multiply that by your new population size of 644.268. And if you take that, 644.268 times 0.013, you're going to get a new number, 8.375. Now, this is the only way to do this. Let's finish this up. So now we started out with this population of 644.268, and we're going to add 8.375 to it. If we do that, add 644.268, you're going to get 652.643. Now, you might be thinking, well, wait a minute. We already solved for a very similar population change up here, that rate of population change. That was only for that year because it's a function of that population size that you started with. If we took the 644.268 and we added this number that we got previously, 8.268, we're going to get a different number. We're going to get 652.536. Because we aren't accounting for the positive change in the number of individuals per year, we're going to end up underrepresenting how many individuals there are. And so that is like, this doesn't seem like a very big difference, But what if this was over the course of, say, 10 years? It's exponential. You're going to see a graph for growth like this. That looks like this. So we'll draw like year 1 is here, year 2 is here. Not a huge change, but by the time you get to year 5, look at how drastic that changes. If you did not take into account the fact that the population that it's multiplying by each year is larger, you're going to end up with a different looking graph that instead looks something like this. But we know that that's not how this is going to work, because this population size, that n, is changing year to year, and we always need to factor that in.